So this lesson is about convolutional neural networks. So we'll try to understand basically what is this convolutional neural networks and also why we use it, what's the difference, and at the latter stage we'll try to see how to implement a CNN or a convolutional neural network also. All right, so let's start. So basically, we'll try to first understand uh, what is the value of a convolutional neural network. All right. To understand this, uh, let me bring down some images, right? Now, if you want to analyze an image, right? So if you want to analyze an image, so let me bring down an image for you guys. So I'm taking this from one of the articles. Yeah, so as you can see in this image of a swan, so swan has certain characteristic features that can be used for recognition purposes. So this, because this is basically image analysis. The swan has certain characteristics that can be used to determine whether a swan is present or not, such as its long neck, its white color, and other things. So we can see clearly oval shaped white blob or the body. So there's an oval shaped body. So you can see like this is being highlighted or kind of a segmentized. And then a long white rectangular shaped neck. So there's a rectangle here, there's an oval here. And then a round elongated oval with orange, what is this, protuberance, so whatever, right? So that is also there in that small oval. But this can be dramatically changed depending on how the photo is being taken. So let me take another photo of probably the same swan, which can looks very different, right? So in this example, as you can see, uh, so again you find that round elongated head with orange, but a black beak, you know, not a orange one. And then long white neck, square shape. So this one is rectangular shape, this is square space. And then oval shaped white body with without large white symmetric blobs. So now see the wings, so it's not symmetric wings altogether. So then it becomes harder to classify, yes, harder to classify the swan, right? So, but the features are present, but it's more difficult for us to pick our characteristic features. So there can be more extreme cases, guys, extreme cases. So let me bring down another example, which can be extreme, right? Okay, so if you look at this one, you can see what the swan is trying to do. So round elonged head with orange and black beak, right? Long white neck can bend around, not necessarily straight, and white tail generally far from the head. So ideally should be far from the head, now it's not. And this is example, small black circles can be facing the camera, sometimes can see both. So that's another, luckily the color is consistent, but you can see the extreme cases of swan classification. So we know as humans, we can identify it, but unfortunately not for the camera. Sorry, not for the computer, right? Not for the computer, right? So this is the reality of zone classification. And of course, never ever forget, swans are not always white. So there can be black swans as well, right? And then of course, to make a bit of a fun, let me bring down a few more worst case scenarios, right? Worst case scenarios. So these are the worst case scenarios. So as you can see, that can be of course a swan, and this is nothing like a swan, and this is not a swan. He's also not a swan. So he's the one who is going for photography, right? So you can understand now. You have seen enough swan pictures. So now if you look of course how we try to solve this problem of zone classification, right? So image processing comes as savior, but there are things that we can do or cannot do. So that's where we can look at normal neural network, right? So researchers use multiple computation techniques like SIFT, FAST, so there are several others, and then connected with neural networks to handle this situation. And of course, you can use things like representation learning to automatically find relevant features, like unsupervised k-means and supervised neural networks. So in this case, neural networks. So of course, we can use multi-layer perceptron, which is the base of neural networks. So which we can use that. But one of the concerns would be of using the normal neural networks. When it comes to image processing, MLP uses one perceptron for one each input, right? One pixel in an image. So you have to use one perceptron. So if there's an image 224 into 224 pixels with three color channels, right? 224 pixels, the height, and then the width is also 224. What would happen is you'll have three channels because for R and G and B, red, green, and blue. So you will probably get around 150,000 pixels, right? So that's a lot. And if you model this with normal neural network, you will obviously need to train this amount of weights to get an outcome. So when you do this amount of numbers, a lot of overfitting can occur, right? That's one of the issues. So of course, training can be quite difficult. So there's no questions about it. Training can be quite difficult. But remember, this is 224, 224. What if these are 4K images, right? 4K images, so 4K into 4K, or rather 4028 into 4028. So that will take years to process. So you can understand even the best GPU computers will not solve these issues very easily, right? So, and the other problem can be there are this thing called translation invariant. If say as an example, so it's called translation invariant. If you try to give an example for it, if a picture of a cat appears on the top left of the image, so if that's the image, let me bring down a picture to explain this transvariant invariant. Let me bring it down. Okay, so if I okay, so this is called translation invariant. So if a picture of a cat appears in the top left of the image in the picture and the bottom right of another picture, the MLP will try to correct itself and assume that a cat will always appear in the section of the image. So this can be a very random thing, but the MLP is trying to correct them. So here clearly, so in this situation, clearly MLP is not the best idea of using image processing. Whether you like it or not, it's not the best idea. So one of the main problem is that the spatial information is lost when the image is flattened into a MLP. So you'll see even in CNN, we use something called flattening. So you'll find the spatial issues going out. So we thus needs a way to leverage the spatial correction. So the spatiality is very important when it comes to handling images with a lot of information in it. So there are so much of usage or use cases also. Later on, I'll get some interesting figures to explain that. So all these situations, as an example, segmentation. So semantic segmentation to understand like what is in the image. So it's so hard for us to do it through MLP, the normal formats of neural networks. So this is, so in this situation, the MLPs are not really feasible. Right? So normal MLPs or the multi-layer perceptrons, MLP for people who have not learned it. So these are multi-layer perceptrons. right? Perceptrons. So you know what are perceptrons? We have learned it. Perceptrons in the neural networks. So this would not be the ideal solution. So this is where, guys, so if I get a quick multi-layer perceptron image, I think we have seen these things. So this is multi-layer perceptron. You guys have seen it. Yep. So, oops. Okay. That's a multi-layer perceptron. So this will not solve all these problems. Okay, this is where, guys, we get CNNs. CNNs comes into play, which is quite interesting. So let me first show you guys something interesting, which you at least have to know a bit. So yeah, first we'll get this. So this is something as research students you are supposed to know. So this is initially came out in 1998. So this is the first research paper on CNN, gradient based. So it's a gradient based one. You later on learn what is this gradients. Applied to document recognition. This was earlier used for document recognition. So Yan Li Quan, and so this guy is famous and all that. So multi-layer neural networks trained with the backpropagation algorithm constitute the best example for successful gradient-based learning techniques. And given an appropriate network architecture, gradient-based learning algorithms can be used to synthesize complex decision surface, blah, blah, blah. And convolutional neural networks that are specifically designed to deal with this variability of 2D shapes. So basically what you get is actually you are getting a 2D image and you're converting into a 3D space. So that's what you do in a normal neural net, convolutional neural network, which you're going to learn a bit later. So this explains how this process works out. Honestly, I have not read this paper, but you can see the base idea of convolutional neural networks. So what you do is you get a image. This is of a text. Sorry, it's of course a text, a character, and then you find convolutions of it. So the convolutions is basically it's coming from mathematics or the DSP literature, digital signal processing literature, where you find two signals and you are coming up with a new signal, a generated signal. So this is also something similar. But here we convolutions by using to generate something called feature maps. So we are extracting some features out of anything or image, or it can be even remember and understand. Convolutional neural networks can be used for many other purposes, even for generative adversarial networks. So many other disciplines we can use it without much of a problem. Even time series analysis. So remember, it's not really understanding pixels, right? So pixels, understanding pixels would be the best use case for convolutional neural networks, but it's not only for that purpose. So once you do the feature map or convolutionals, we have to do something called pooling. So this doesn't really show the word pooling, but it's shows something called subsampling, which is somewhat similar. And then you have to do something called flattening, which is not shown here. And then you can push it to a normal neural network, right? So, but anyway, you can see this is a very long paper of 46 pages. Obviously, this had gone into a journal, I believe so. Yeah. So at least go through it and just flow through. That also would do a bit of good. All right. So that is basically about the intro for that. And now we'll jump in to understand what is a convolutional neural network, right? So okay, let's start discussing about that. Right. So first of all, you have to understand any type of neural network does something called function approximation, right? So what it does is something called function approximation. So as you can see, oops, it's not going to work. Let me take the image out of it. So what you do is basically a function approximation. Neural networks are universal function approximators, so that a means neural network can learn an approximation of any function. So y equals fx. So that's what they do. And so this is a good example for approximation. So when you get an image like this, so you can approximate it to 2. So that's basically what a neural network would do. Right. So the next thing is when it comes to image recognition, right? So image recognition, uh, we obviously know we can use neural networks. Uh, so this can be achieved by neural networks, but the problem is if the image a lot of pixels. We discussed about it. Then you are in bit of a problem. So I think I have given you an example also. I have another example which I can share with you guys. If the yeah, if the image is consisting of this amount of pixels, so you can see 3 million input parameters to process, which can be a lot. So it needs a lot of computational power to handle that. So which can be a problem. So that's where the CNN comes in, and CNNs can be used for these purposes. So let us discuss some of these purposes. Of course, you can use it for object detection. So as you can see here a car being detected, a horse, a person, a dog, and a cat. So all these things can be done using convolutional neural networks with ease, right? Even though the concept is a bit complicated, you can obviously learn that, and also you can use it for edge detection. As you can see, this leopard. So you can easily decide on the edges. So that's another cool thing that it can do. And then we go into this other beautiful concept of semantic segmentation. So as you can see here, you can find out a table with a lot of other things, but you identify meaningfully it's a table, and there you find a lot of people together, so it's persons, and also there's a TV. So that sort of semantic segmentation can be done later on. If time permits, we'll understand, okay, there's a nice implementation of this called mask RCNN or fast RCNN or RCNN, which specifically built to do semantic segmentation. And then of course image captions. So you can see uh, here you can say a man in black shirt is playing a guitar, so that's captioning. And construction worker in orange safety vest is in working on road. And boys is doing a backflip on water boat, or sorry, lake boat. Yeah, so that's something else you can understand. And yeah, then you can do questions and answering. So that's another cool thing. What kind of store is this? So you can say bakery, art supplies, bakery, grocery. So likewise, you can do few things. And then only problem to achieve any of these things would be computers see images different than humans. So this is the problem. So computers can only see these digits. So this is where you need to come up with an interesting concept of CNN. Right. So what we try to do here in CNN, we try to break the image into kind of a workflow, right? So initially what you can do is you can take the image and you can convert it to convolutions. So convolution is, like I said earlier, it's a different perspective of the same image. So we'll try to see how we do it step by step. So we can get the convolutions first. So we can get the convolution. So we use something called filter or kernel to do that. Don't worry, we'll understand it. Once you get these convolutions, we'll try to get different perspectives on the image. Right? So initially, like you look at the image through cohesive manner, where you can see the finer details like edges or the curves and all these things. And when you move in the next step of a convolutional, you can see other things like real faces and things like that. So to drill down the data rather than sending all the data at once to a network, for a neural network, right? So this is your neural network. So basically now if you get the base idea is this: you have this amount of 1 million amount of pixels. You can't feed of course 1 million pixels into this, but you have to convert it in a way, spiraling in it a way where at the end you will be able to convert it to 3 pixels and send it to the neural network for the input layer. So this is a dense layer. So basically that's what you're doing. If you are trying to do the other way around, it will take like a MLP, it take a long time. So to do this process, you have to do it in a logical way. That's why first we use convolutions, right? So convolutions can be created. So these are different functions in that sense from the exact image it is given. So we'll see how to do the convolutions later. So I told you we use something called a filter and do that. And then we use activation functions to correct it. So once you do use activation function, normally ReLU function is used a lot in convolutional or CNN. So once you get it done, so then you get a very, what we say, a more accurate value. And then what you do is we use, as a second step, we use something called max pooling. So again, we'll try to understand it in a later stage, what exactly you do in the pooling stage. So that's basically a reduction of the image size. So the thing is, convolutions will not definitely reduce the image, but it tries to identify the features. So basically, outcome of the convolutions would be to come up with a feature map. So you get different types of features. That's your objective in the convolution, but not to remove the dimensions or reduce the dimensions of the data. So to do that, you use max pooling techniques. So max pooling will reduce the amount of data, right? So these two coupled together, we can run parallelly for a few times. So as an example, try to understand, you can do a convolution C1 and a pooling P1. So you get now a good set of feature set which you can send to this guy. But see, if we are not convinced enough, this is narrowed down. So you can go with another cycle with another C2 and a P2. So you do a convolution and you do a pooling again. So now we are in a format where you can send it to this guy. But the thing is, these are all matrices. You have to flatten it out. So to flatten, you use this full. Once you flatten it, you can send it to a fully connected layer. And at the latter stage, you can use, as it says, softmax to get your final outcome. So this is basically the overall picture of what you say as a convolutional neural network. So again, to sum it up, so basically you have two-stage process. We get convolutions. That is a different dimension of the image. Like I said initially, you can look at the features, then you go deep into it, you find other things. So when you go with convolution pooling, you try to see it like naturally how it happens. So to demonstrate it, let me get a small video. The only concern that I have is because I'm going to put my videos in YouTube. I don't want to get a copyright, so I have to carefully get this video. So this is sort of a very interesting video. So this is called Deep Dream. Deep Dream. The only thing is I would try to filter this out for Creative Commons. Otherwise, I would have issues of playing it back. So normally we can't play back other people's videos. So this is Creative Commons, so I can really use it. And artificial neural network dreaming. Twitch plays large-scale deep neural net, LSD. Don't know whether it's a CNN altogether, but this is the idea. I don't know whether this will clearly show the representation. So what happens is initial stages. You try to see the base details, not like the holistic idea, but the here and there details, the edges, and then nodes surrounding. But when you move in, I'm not going to run the whole video, you can watch that. You try to see what's there. So this is really how not the brain understands things, but the computer understands things. So when the convolutions and poolings are going around, you tend to see the real images inside. So you can see some images appearing. So the computer understands them then and there. So please, I will share a video which is you can watch, which I cannot run here, which gives more clearer view on this idea. So, and this is also an interesting or fascinating idea, like how do you capture these images, but there are techniques to capture this when you're running your own neural network, training your neural network. So which is quite cool. So it's called Deep Dream. So you guys can check it out. I'll close that. Okay, that's fine. So hope that this is clear for you guys. All right, so now, yeah, so now we'll move on. So now we'll try to understand what are the main components. So we have looked at it. So let me try to bring down slide. So as you can see here, convolutional neural networks have two main components. So first part is called the feature learning. So this is where actually we do use those layers, special layers, convolution layers or the ReLU for activation and the pooling layers, right? There you learn edges, shades, lines, curves in this layer. So once you do that, so that will be fed to the normal neural network. So you have a fully connected layer. So that will do the classification part. So don't get it wrong. The initial layers of the CNN always do feature learning. The classifications happens thereafter, which basically a normal network. Once you start implementation, we'll try to understand it. So to get a more clearer view on this, let me get this image. So this will basically show you the idea. So as you can see here, once you get an image, so that will be converted to a convolution. So as you can see, convolutions are always defined as 3D, guys. So basically what happens here, you scan through the image, right? So your image would look like this. So what you do is, these are the pixels, guys. And then what you do is using something called filters. So filter can be something like this, or some people call it as feature maps or kernels. So you are using a kernel like this where I can capture part of the image pixels, and then you are going to go through this in a sequential order. So once you're scanning, it's like scanning, like you're going in this direction, again, another scan, set of scans. Once you do the scan, what you're going to do is you're going to create an image like this with a different dimension. And then these filters will be applied again and again. So once you have another filter, okay, there will be another dimensions created. So likewise, when you do this process sometimes, now you get a new dimension set with a depth. So you don't have a depth here, there's a height and a width. Of course, there's a height and a width and another depth parameter also added to this. So your 2D becomes 3D. So there's a lot of maths here, which I'm not going to cover anyway. So, but understand this is what really happens. So by having this three-dimensional methodology, you will be able to see more features or finer grain features in your feature selection. So that's what you do in the convolution. That's why obviously convolutions are shown in 3D. So then what you do is convolutions have a lot of data. So you have to drop down the data. That's where you use pooling. Right? So we'll see example of pooling later on. Don't worry, understand proper. And this you keep continuing. So this is one process step, and that can be repeated again. So this is another one. So the convolution and pooling again be done. Remember, there's a ReLU in the middle. So the activation should be done for the weights. And then you do the second iteration. So you can do more iterations, right, depending on your need. Right? So in your research work, you can do this. And then, of course, guys, you have to do flatten. So this is a model which you cannot feed directly into a input layer. So you have to flatten this out. So once you flatten this, now you have it in a one-dimensional array, and that can be sent to a fully connected neural network. So this can be a normal neural network, and then it can bring down your needed classification. So this is to figure out dogs and cats, so it will say either dog or a cat. If this is to identify MNIST numbers, you can say it's 1 to 9. Or it can be about time series prediction, that also can be defined without much of a problem. So hope that is clear. Right, now we dive in to understand what would be the convolution layer does. Right? So we are now jumping in. Right. So in the convolution layer, what we try to do is We are trying to learn features. So that's the phase one. We have learned that earlier. So it's basically identifying features. So every image can be considered as a matrix of pixel values. And as you can see, it's considered 5 by 5 image whose pixel values are only 0 and 1. See, but this is like an image. But do understand real world can be much different. You can have your values ranging from 0 to 55 because your R value, G value changes from 0 to 55. But you can of course change it or cut it down. We have done it, one of those classification problems. You can basically convert it to ones and zeros. So that's not a big deal. Right. So once you have an image, so now what we are supposed to do is we have to use a filter like I explained in the previous previous slide, right? So we can use a filter. So the filter, what the filter tries to do is, filter tries to go to this image and try to come up with a new convolutional layer. So the input image is multiplied by a filter. So it's basically a multiplication to get the convolved layer or convolution layer. This filter differs in shapes and values to get different features like, so okay, the purpose is different types of filters can be used, or these are kernels, to identify edges, curves, lines, and other things. And these are sometimes called kernels or feature detectors. I think I called it feature map, sorry about it, it's called feature detector. So that's quite cool and quite interesting. And depending on your situation, you can use different types of filters. So there you find different types of filters. So to identity, you get this sort of filter. You have only one in the middle, and you get the convolved image like this. For edge detection, you can use all these filters. So you can see you can do ones at corners, and there's a 2 minus in the corner, and there's a -4 in the corner. These are for edge detection. So what happens is, like when you do this matrix multiplication, it converts your original image to this sort of converged image, which is cool. And then to sharpen, see, there's another one. So these are all maths, guys, right? All maths, algebra, right? So nothing else. Box blur, you can do this. And don't ever think of why is that. If you want to do that, learn algebra and then learn it. So for the moment, understand the use case. So, and there's something called approximation of something, that's called Gaussian blur. So just consider that, right? And then of course next one is to understand the filter size. Depending on what you're supposed to get, you can use different types of filters. This you have to define in your implementation of the neural network, guys. So this can be quite useful to know, right? So what sort of filter you have to use. So you can do a lot of experiments with CNN, right? Okay, sorry about it. Right. Okay. So filters with different sizes, right? So now, if you look at a simple kernel or filter, so you can have a 3 by 3 filter. Some features from the input image to pixel values in input image. So you can see all ones in the appendices. What I said, I'm not sure what is that. So these are the ones, right? So it's a bit of a different one, right? So so now if I try to get a let me see whether I can get a image of this working, so you'll understand it better. Yeah, I have it here. So this is, I'm taking this article from Towards Data Science. So this is 2D convolution in operation. So you can see this, the filter is moving, guys. So filter can be 1, 1, 1, 1, 1, 1. So they do the matrix manipulation. You're getting this new convolution. So you can see, of course, you will get a customized image now, or the dimension now. But when you do this filter several times, so you can get the depth as well. Right, so this kernel repeats this process for every location it slides over, convert. So you can also control how this things moves out. That's also you can control. That's not a big deal. So you have to define it in your programming code. This is called striding. So how this striding works, one after the other or two after the other. So likewise, you can define it, right? So when you're doing this process, so there's advanced, not advanced option, but there's something called padding. So that also can be used to trimmed off some of the edges. So that's another technique. So you can see this is the option of padding, which is used as a common concept. Then of course this is another option of this is called striding, right, which I talked about. And then of course that's basically it. And this is the one which you get the depth, also you get the channeling, multiple channels can be used, right? So yeah, so this is what you do for multiple channels, and you can get your outputs. So likewise, you can send these convolutions together. And once you do the convolutions, later on you'll understand you do something called pooling. So remember, these convolutions can be a bit complicated when you want to do it, but the ones that we do can be pretty straightforward. Right, yeah. So basically, yeah, this article can be a good read. All right, so keep it aside. Now we got the idea clear. Right. So now we have it here. Now what we try to understand is that filtering process. So we have looked at in the animation. Right, so each value in pixel of input image is multiplied with the respective value. So you can see this particular filter is now moving around. So you have seen that. Yeah, so then you can get the convolved feature. So this is the convolved feature. So we have discussed about it several times now. Right. So now the result of the convolved feature depends on 3 parameters, right? So this convolved feature can be a bit tricky, right? So we'll try to see what are those features that we need to address, right? So the first one is the depth, right? So we have something called the depth. So let me bring, oops, what happened? Let me paste it here. Oops, that's bad. That's not going to work. So let me. Okay, so yeah, so depth is in the above input image, we just considered image the depth of 1. So we have just seen the previous slide a depth of 1. But most of the inputs will be depth of 3, which is of 3 channels. But you can go more, you can, depending on the number of filters that you use. And of course, stride is the number of, so let me take that as well to make the slide clear. Oops. Okay, stride is the number of pixels by which we slide our filter matrix over the input matrix. When the stride is 1, then we move the filter 1 pixel at a time. Right, so hope it's clear. So your image is somewhere here. You have the filter here, and then you move 1 pixel at a time. So that's the next stride. Okay. When the stride is 2, then the filter jumps 2 pixels. So especially you will see this stride is 2, especially in the pooling. So I'll explain that later. Having larger stride will produce smaller feature. Now, of course, you can understand. So when you have larger strides, you get a smaller image at the end, right? And of course, the other one is the one that we have not discussed much, which is called the padding, which is used especially when you want to filter out this unnecessary edges and all that, right? So this also can be a very useful one when it comes to your designing of the convolutional networks. It's the key of how many pixels you add extra to the image. Mostly padding would be 1. Right? So we go with the default padding in our implementation. All right, so that's clear. So that's basically what you do in convolutions. Right. If it is padding is 0, you will get a basic image of this nature, right? So if the padding is 0, all right. Okay, now we look at the max pooling, right? So we look at the max pooling. All right, so now what you see here is the max pooling. So what you do in the max pooling, you again use a filter. So in this filter is a 2 by 2 filter. This is quite easy to understand. The slide is 2. Always go with 2, right? So now what you do is this is called pooling, meaning you are converting this into a new layer. So max pooling means if you have, now these all pixels or values. So what you do is you get these 4 values 1, 1, 5, 6, and you get the max out of it, which is called max pooling. So then you put 6 here. So now you might think, should this process lose some of the data or like destroy some of the, yeah, true, but that's all right. So that's all right for our accurate identification. So this is also reduction of data. Try to understand the idea of doing this max or the pooling is reduction of the data, unnecessary data, right? So this max pooling is basically getting the maximum. And then of course you have other methods called average pooling and few other methods. Average is getting the average all of this. 1, 1 is 2, plus 6 is 8, 5, 13, plus divide by 4, whatever the number which will happen here, happen to come here. But that, they have realized by doing experimentation, max pooling can be better, right? So that's why they use max pooling in the current situation. All right, so now when you put all this together, right, so now you understand this is not rocket science, this you can understand. So this is how the but remember, we have not discussed the mathematical foundation of each operation. That's for you to do, right? So now our CNN network looks like this. Input images, you have convolution. As you can see the dimension, the depth, and then the pooling. Pooling also have the dimensions. Then you do the other thing, the final thing called the flattening. So when you do the flattening, guys, you can convert it to a one-dimensional vector, and that can be directed toward the normal ANNs. So that's how basically it works. Just to give you few points now, if you want to understand that concept of uh, convolution a bit, now this is basically the same logic. Uh, the image, so this is from the MNIST data set. So there you can see uh, the image clearly, right? So the image clearly, and then the filter applied. Now this is what happens to the convolved output. So now only thing I have to understand is this is 28. I don't know whether it's clear to see, guys. This is 28 by 28, but this becomes 26 by 26. We'll understand it a bit later. And then you can apply multiple filters like this. Then you get this. You can see the depth, which is cool, right? So this is without padding. So you're not worried about the padding part now, right? And then the next one. All right, so the next part would be to get into the, so next part would be, if you look at this, the activation, right? So this is the activation. So normally we do use non-linear activation. So there are linear activations also, but we use non-linear activation here. So ReLU, or there's another one called leaky ReLU, used for activation functions. So we are not going to discuss this, but this leaky ReLU solves the problem of something called dying ReLU problem. That's no importance for us at the moment. So you do the convolution first, then the second ReLU, and the max pooling. So it said that it's okay to do the other way around also. Basically switching this to, that would give the same result. So mathematically also there's a way of explaining this, which I'm not going to do anyway. So then this is the pooling. So basically, like I told you, we use the pooling for downsampling. So we use two hyperparameters here: dimension of spatial extent. So that's another way of understand the depth, and then the stride, right? The stride. So stride is 2 by 2 in our examples. So you can see the max pooling in action again. So which is not going to be hard to understand for you guys. All right, so that's cool. So the next one is about the fully connected layer. So that's where you have to do the flattening. So this you get, sorry, you can't see it here. This is your dimensions, the 3D volume, and this will be flattened to 5000 some number, right? That's what happens in the flattening layer, right? All right, so that's understandable, right? Hope it's clear. And okay, finally you get this beautiful thing, which is the ideal convolutional network. So you guys can see that's only one part I had to explain here. So this is the same thing we have discussed over and over again. So you get your convolution layer, the stride of this, and you get this pooling. So this is your convolution layer. 26, 20 is 32. 32 filters been applied. So you have the dimension depth also. Now it's 3D, 2D to 3D. Right. So 26, why it's 26, guys? So this is the reason why it's 26. So, all right. So that's not the one that I want to take. Okay. So this is the width and the height plus 1. So that's how we get 26. And the depth is the number of filters, right, that you apply. So that is specifically for the creation of the pool, so the convolution layer. And finally, you have to do the same thing. Now this time, the only difference is coming up with the max pool, right? So that you calculate in this particular way. So when you get the max pooling, you get the stride as well. So please remember this. I'm going to ask some questions for the exam. Whoever listening to this for the coursework, others like who are going to learn this in my YouTube. Okay, that's happening now. Anyway, something had gone wrong. Okay, so in that sense, try to understand this, how you calculate it. So that's the logical side of it. All right, so all seems fine. So that was almost 1 hour of content, right? So this is, if you can remember, this is the base side, but remember this is in a very nutshell what's happening in a CNN, but which is really important for you to understand, guys. Okay, so it's good if I would have asked about any questions which you guys have. Unfortunately, we can't ask for questions. But just to give you a bit of nice representations of convolution, so there's another nice graph. So now hope you can understand. Right, so this is the operation, right, which happens from source pixel to destination pixels. So this is how the maths works. All right. Okay, so I think that would be good enough for the moment. So right now what we are supposed to do is the implementation. Right, so now we'll be using Google Colabs to do this. So we have learned the basics of Colab different times. So now we'll try to use Colabs to do this one. So, so I'll create a new notebook and we'll do a quick CNN. So, but see, like understanding CNNs can take a bit of a time. But don't get me wrong, right? So I have done what was a very uh, high level overview of CNN, but there's a lot more to learn about it. So this is CNN intro, right? So now we'll try to do a quick demonstration. So this one basically does a simple convolutional neural network to classify. Oops, where's my text segment? Okay, it should come here. All right, this tutorial demonstrates a simple convolutional neural network classifies CIFAR image. So CIFAR is a very famous image database dataset which is in the net, so which you guys can use. Uses Keras sequential API. We have used it earlier, and the TensorFlow backend. All right, so that's cool. Next to the code, so we are going to import TensorFlow. Sorry, make sure that I do type things right. TensorFlow STF, and then I need to get TensorFlow Keras import data sets. So these are things which I need: layers and models. And finally, import matplotlib. I don't know whether we don't have. Okay, yeah. So matplotlib as PLT. Okay, that would do. So that's all the imports that I'm supposed to do. Take a bit of a time. I will go to the next step. So this time we are going to download the CFR dataset. So it contains, guys, 60,000 images in 10 classes and 6,000 images in each class. The dataset is divided to 50,000 training images and 10,000 test images. All right, so that's basically the format of the data set. All right, so if you have never seen the CIFR10 data set, okay, so let us quickly look at it. This is the data set. I think we have not used it earlier. So this is from this Toronto University. I would have checked the wiki page. Yeah, so you can see airplanes, automobiles, birds, trucks, ships. Yeah, so you have the details here, guys. So all cool. So now we'll write our code. All right. So now what I need is to get down all the data loaded. So of course I can directly call CFR load data function, and then I can call the load data function, and then I can put it into train images, train labels, test images, test labels. So I have put into those classes. So that's fine. So after that, one thing you're understanding, we talked about things, all the pixel values are from 0 to 255. So we have to put it into zeros and ones so you can normalize it. So we talked about it and we have done it in an earlier lesson also. So this is silly, but you can do. So let me run this. It might take a bit of a time to download stuff. Yeah, they're downloading pretty fast because it's all Google stuff. So which is cool. Yes, it has already done the work. So this is to download the content. All right, that's good enough. And then we have to verify the data. So to verify the data set, whether it looks correct, first of all, we have to plot few images. That's what you do as good machine learning engineers or cybersecurity machine learning engineers. That's what you do. and display class name below the image. So this is something that you're supposed to do. Right. Okay. So that as a verification phase, code. Right. So initially we have to put the class names. So now we have seen the classes of images, aeroplane, blah, blah, blah. So these are the class names, right? So then we have to plot it. So to plot, we use, so we get the figure size of this. Oops, sorry. And then we have to write a for loop, and inside that we can define all the details of what we are supposed to plot, right? That's fine. And also you can put labels for the plot. So those are the labels that we require. And finally, the most important command, plt show, plot show. Right. So let's see whether we can get our images. All right. So we can see 5 by 5, and you can see the labels, the frog, but you can see it's not very clear. So, but still it's okay. Right, so now we have our data set. Everything seems to be ready. So now what we do is we'll try to implement our convolutional layer. So this is the structure of it. All right. So if you read through, you can understand 6 lines of code below define convolutional base using common pattern, a stack of contour and max pooling layers. So these are the 2 things that we're using. And as input, CNN take as tensors of shape. So we have already defined it. And if you are new to these dimensions, color channels RGB. So and the shape would be 3230 by 3. So it's not big deal. So now we are going to write our code. Okay. So first, of course, we define our sequential model, Keras model, and then we are going to put our first convolutional layer, guys. All right, so this is simple. So you're going to say layers 2D, and this is 32, and 3 by 3 filtering, right? And the activation function is ReLU, and input shape is 32 by 3 channels. So it's a 32 by 32 image, and it's 3 channels. So that's quite easy to understand. So now what to do? So now we have done the convolution layer, and then what to do? Yes, you have to do the pooling layer. All right, so then you define the pooling layer, max pooling 2D and 2 by 2. That's that. So now can we go and do the flattening? Yeah, of course we can do that, but it's important to do another round of convolutional layer and the max pooling layer. So we'll do another iteration. So that would make the model better. Right. So this time we do 64 and yeah. So then 2 by 2 again. So we'll from this. Yep. Seems to be all right. So then what we need is the model. So how to get a model? So we can get the summary of the model by saying model summary. All cool. So we run that. So we should get our convolutional layers architecture. So you can see this one, how many parameters, and then again you get this amount of parameters. So you altogether you have 56,000 parameters, right? So now you can see that the output of every convolutional and maximum layer is a 3D sensor. It's a 3D sensor. So you can see 3D is of course 3D, right? Of shade, height, width, and channels. The width and the height dimensions tend to shrink as you go deeper into the network, right? The number of output channels for each convolution layer is controlled by the first argument. So it's basically the channels, right? Output channels, whether it's 32 or 64. and as the width of the height shrink, you can afford to add more output channels to the layers. Right. So now it's now we have done with the convolutional logic or the features. As you can see, we have done the features, guys. If you can remember, so this part feature learning we have done altogether. Now, sorry, features. Now we have to do the classification. There's one step missing, which is the flattening, which will come to that. So I'll add text here. Okay. Add the text. Okay. That's okay. Now the code. So basically, what you have is add dense layers on the top, right? So to complete our model, you will feed the last output tensor from the convolutional base into one of our more dense layers from classification. So that's where you do the flattening. So you have to do the flattening, right? Okay. So to do the flattening, it's not that hard when it comes to programming. So you can see you can add the flatten layer, and then you can have a dense layer, right? And then you can finally have a output layer of, so this is the hidden layer, guys. This is the output layer. So it's quite simple. So now what we need is, once it ran, so you can have another code segment. Still it's running. Okay. Now I can check the model summary. Okay, now we can see everything, including my dense layer. So altogether, you can, these are the parameters. Right, now comes to the cool thing. So now it's basically, yes, what you have to do now. So you have to develop our, sorry, not develop, you have to develop our model. Now we have to train it, compile and train it. So this is the way to compile our complete deep neural network. So we are using optimizer Adam, and also there's a loss function use cost entropy, and because this is at end of the day it's a classification, guys, and the matrices at the moment accuracy I told you that day how to use MSE and all these things, and now basically the compilation model is done. Now we have to call fit, or you have to train the model. So use the fit function. So these are your values and 10 epochs, and then the validation data sets. So now we'll check the accuracy at the end. So now everything goes fine. They should get trained. So you can see the epochs are running. Right, so it's running cool. This is at Colabs. It will not affect my computer. You can see the RAM disk and things are running. Okay, let it run. So still it's at epoch 1. So you can see the accuracy is improving, right? Yep. So now what I need to do is evaluate the model. So I have to wait until model get compiled and trained. So once I do that, I can plot basically the accuracy. And put the epochs and accuracy and see how the accuracy changes. The bad thing is it seems to be running slow. Still in this first epoch, now the second one. All right, that's only the bad part. Okay, so I'm going to, once I finish this, I'm going to finish the session, and then I'm going to have another one which basically do some other interesting CNN models and mask RCNN, and then how to use TensorBoard. We haven't done the TensorBoard, so we'll see how to use the TensorBoard as well, which is also quite interesting. All right, so it seems to be taking a bit of a time. So now I can't stop it anyway. I can stop it. I'll wait anyway. So I can post the video and come back if needed. Yeah. I'll do that. So I came back, still it's running, but I wanted to show you some good resources which you guys can use. Let me bring down this YouTube, and here you find first one is this deep learning book. It is quite useful, so you can get a copy of this, right? So it's highly recommended to read this chapter for you guys from the deep learning book. It shows all the related concepts and also the theory and also the maths. So this is the max pooling. So all these things are explained pretty well. Okay. So this particular chapter is available for free to read, which is a good thing, and it covers all the research and also, let me check. Let's see, the fourth, we have to wait a bit longer, so let me show that also. So please do read it and get the book if possible. Right. And then there's this nice paper. So of course I have not touched on the research side of machine learning yet. So this is quite a new paper, 2016. So unsupervised representation learning for deep convolutional generative adversarial network. You probably have not learned about generative adversarial GANs, which are popular. So we can use CNNs to prepare data for GANs. So it uses computer. It says this work we hope to help bridge the gap between success of CNNs for supervised learning and unsupervised learning. We introduce class of CNN called deep convolutional generative adversarial networks that have certain architecture constraints. And it can be used for unsupervised learning as well. Training on various image datasets, we show convincing evidence for deep convolutional adversarial pair lens. So we'll touch on this generative adversarial networks first later, but this is a good read for you guys. All right. And next, there's some resource about flattening and also difference between CNN and MLP, which is quite important. So there'll be questions on those lines. So please look at them. Yep, especially this is very important because we have covered a bit on that. So this is the average pooling layer. So we use max pooled. So these are also a kind of a similar network layer. So now we have created one. You can see the same logic. So this is the global averaging, which is not used much, but still, yeah. So, and also there are a lot of usage for localization, identification, classification. So all these things we use CNN. All right. So, and also the difference between convolutional neural networks and multi-layer perceptrons. So we have discussed it actually. And we said multi-layer or MLPs are quite difficult to use for these problems. And what else? Okay, and see, this is like visual to generate the CNN, which can be useful. Probably 2 more minutes. You can hang around. So it's a script to illustrating CNN. Yeah, so quite useful, no? You can get your model like this, right? So this can be quite useful. And yeah, convert Keras sequential model. Okay, and you can get all the details, like hyperparameters and everything listed down, which is cool. So this is famous AlexNet. So, and you can search for these things, whereas AlexNet is used. So what sort of CNN used by Google, Apple, yeah. So those things are quite famous these days. So yeah, and Geoffrey Hinton, yeah. So okay, you should know that Geoffrey. Yes, the network top 5 error, blah blah blah. So this is quite a famous neural net an extent, and it's a FNet and other things, autoencoders. Yeah, there's a lot of cool things. Okay, so I'm going to close that. All right, now we have to wait a bit longer. Um, so probably 1 or 2 minutes. We'll hang around. So this is the one of the problems with deep learning, machine learning. You guys have to wait, and sometimes wait quite long. And see, if you did a small mistake, now you have to wait longer, right? So this is where you need to have good setup to do things faster. Yes. And guys, like we talked about Pickle and JLib and JSON, you want to save your models, so that can be quite useful as well. Yep. Hang around for 1 minute, then we are good to go. So remember, for CNN, there's plenty of resources in Google if you search for, right? So do some studying, because CNN RNNs are quite famous these days. So good you know the basics. Right, the last one in a bit. Come back. Okay, so almost through. Yeah, that. Now we'll be able to plot. So it's been trained. The code. Yep. So this is what I want to get now. So let's do the plot and see about the accuracy levels. Yep. So fine. So the accuracy is quite good. It's quite good. So if you do a bit of changes here and there, now we know how to do these things. You can see the epochs and accuracy. When the epochs moves out, the accuracy, of course, if I run only one, somewhere around here now. So if you do, of course, you can understand like the way it's heading, it won't have a rapid growth like this, but still with the epochs, it can go up to like 0.9 if you do like 20, 30 probably. So that's basically the accuracy level. So at the moment, the current accuracy is as here as of this one is 0.706. So this is around 70%, not bad for few lines of code, guys. But so we'll try to improve this, of course, right? So it's quite useful, right? So that's good. So that's CNN. That's CNN. Start of CNN. So just observe the rest of it and do this process again, right? Do this process again. Right. So I can share you this Colab notebook, or you can do it again, right? So no worries. All right, so meet you with the next. Thank you.